Hello, my name is Akindele Yamotosho, and I'm going to be doing a presentation on acetylcholine sterase. Okay, I'm trying to get it right. Acetylcholine sterase is an enzyme found in our nervous system, and its main job is to break down a chemical called acetylcholine, which sends messages from our nerves to our muscles. So, after this message is sent, acetylcholine sterase comes out comes in and clears out kind of like of it comes in and clears out all the extra stuff like a reset button so that another message can be sent. It is found in the sympathetic cleft between nerve cells, especially in neurons that use acetylcholine, and it's found in humans and also other animals. And what happens, what the problem is, serine is a nerve agent, and it's a dangerous nerve agent that is found in a poisonous in a snake. And instead of this entire protein mutating, serine actually just attaches to acetylcholine sterase, and it just prevents it binds to it, a part of it, and it prevents it from it binds to its active site where everything happens, and it prevents it from actually combining with other things to actually do its job. And when it's there, it just blocks it from doing anything else it needs to do. And this would mean that acetylcholine doesn't get broken down. So it keeps sending the message that it's trying to send to the muscles, but there is no new message. So it causes muscle spasms. It can cause confusion and even death in some cases. So normally, acetylcholine sulfase would actually be able to do this like normally, but because um, it normally has serine, a protein called serine in its active site, which has an OH group that helps interact with acetylcholine and break it down. But when serine binds to the serine, it adds something called a phosphorus group, and that completely blocks the OH group from stopping the enzyme and stops the enzyme from working. So here is my 3D model. You can see it. So the blue is the acetylcholine series, and as you can see, this is what I saw as a diagram, as what it might look like as 3D model. Not this is as a yarn because that's what I had to use. This is it accepting a binding agent, but here you can see the yellow is actually the sawing the snake venom, this toxic snake bite, which actually is binding to it instead of the normal serine, and it's preventing it from actually connecting with the acetylcholine surface, and it actually just stops it from connecting with um, connecting with the acetylcholine and the serine, and it just prevents it from happening. So when this enzyme doesn't work, our nervous system normally just gets overloaded completely, and it just prevents any other action from being taken in a sense. So because of that, that's why it's actually so dangerous. Because if you can't move, you can't eat, you're not gonna be able to do anything else about that. So in I'm gonna just show my diagram because this part, I'm gonna explain why I'm saying it. So I'm gonna say again, this part is the snake toxin. This is the where it binds. This is where normally the normal functionality, normal things, the normal enzyme would bind to it, but instead the snake venom is preventing it from binding. It didn't do anything necessarily to it except it binds to this agent. It's not like it's causing damage, which is why it's not really a mutation. It's not directly causing damage, but it is causing damage at the same time because it's preventing certain and it's putting certain in the I apologize, acetylcholine from actually essentially connecting to it. So, see, I think I can get it fully. This is it. This is it connecting. Um, but yes. So that is my 3D model. And to wrap it up, acetylcholine surface is essentially controlling signals, and serine is chemically blocking it, leading to serious injuries or even death. So thank you for listening to my presentation. Have a good day.